slide that we had last time, and people were confused about what 4 numbers were in the last column. So I divided them into 4 columns. Slide 13.33. The last column has become 4 columns. So this is a complete table entry with the destination, sequence, hops, and next. And so you see the entry as it should be. And that was one thing. Second thing, I fixed all the bugs about rrep and rrec. So this is now correct slide. Everything should be correct so far, unless we find some more bugs. Okay, that's all I have to say. There is no material change except all the bugs have been fixed, and it has been clarified as to what the 4 numbers were. There was a dash between the 4 numbers, and that was causing some confusion. Okay, any question about that? None. So we move on to then the next one, which is DSR, slide 1337. So DSR is the another alternative which is allowed by ZigBee, and basically, as the name says, it is source routing in the sense that the complete route is put into the packet. So all the hops are put into the packet. So the routing database actually consists of complete route. So basically, when you have a destination, you also have the route to that destination, which you put into the packet. And obviously, just like before, every entry has an expiration time. If it expires, then it is timed out. If the route is not available, then you send a route request just as before. The route request is very similar to the previous one: source address, broadcast, and then route request is the type, request ID, destination address, and route record. The last field is variable length. So the last field is where everybody puts their address as it moves along, so the route builds up in that field. So the length changes at every hop. Each neighbor adds itself to the route in the request and forwards to all of its neighbor only first receipt, and does not change the source address. So the source address remains the same. If a node knows the route, it appends the rest of the route and returns the route reply. So this thing is, it doesn't have to go all the way to the destination. If the next hop knows how to get there, you will get a reply from them with the rest of the things filled in. And route rep goes back along the recorded path. So that's another thing, is just like before, it is unicast. So the people who do not get the reply may not know anything, but wherever the shortest path is, the reply will go back to that and they will get it. All nodes record the path in rrep and rrec. So this is very similar to AODV. Everybody examines both rrep and rrec, and then whatever information is there makes a notes of it. Now I must point out, even though I'm teaching DSR after AODV, DSR is older than AODV in ZigBee. It was there before, and there were some inefficiencies, so AODV is more efficient than DSR. And in particular, for example, all this variable length route and all that is not very convenient, but it is there. Okay, so I will take an example. So the example is the same example that we had before. Node 1 wants to go to node 10. And so sends a request to 2, 3, and 4. And says anyone has a route to 10. And then 2 will send to 5 and 7. Now it does not send to 1 because it already knows that that request has 1 in the path. So that is recorded in the packet. Okay, thank you. And then, so that is one main thing, is that, in the previous case in AODV, it went back and it was discarded at the after receipt. Here it is not sent, so it is discarded at the, before sending. So this is a positive aspect. So the key point I was making before was that the main difference that you notice one so far is that the message is not sent to the host which has already gone through, right? Because the route is in the packet. And so the route request is not sent back to 1 from 2, whereas in AODV it was sent back and then 1 would discard, noticing that it already knows about it. So then node 3 will send to 5, and because that's the only other connection left after 1, and 4 will send to 6. And the rest will go just like before, a table I have put here. And this table in the new case, you will notice that the previous version of this slide had the same bug as before. rrec and rrep were wrong, but now it is all correct. So this version of the handout that you have, you may just want to make sure that you keep this and discard the old one. But so the new rec arrives at 1, it is sent to 2, and then the route record becomes 1-2. When it goes to 3, it becomes the route record in that packet is 1-3. When it goes to 4, route record is 1-4. Now so all the 1 hops are covered. Then we go to the 2 hop nodes. 2 sends it to 5. In that the route record is 125. 2 sends to 7 at the destination. Now this is the route record at the destination basically. At 7, the route record becomes 127. And at 3 sends to 5 again. And now here is another interesting thing. 3 sends to 5. 5 notices that this is a duplicate ID, but it is not bad. It's the same hops. Okay? Since it is the same hops, it keeps that record as well. So now it keeps 2 records. So it has 125 and 135. There are 2 ways to go to 1 from 5. And this is important part, is that in AODV we had just 1 record. Here we have multiple records. So either you can say caches or adds, but the thing is both of them are equally good. Okay, if it was 4 hops, it will discard it. But since it is the same, since it is 2 hops, it will just add that one. So it will keep 2 hops nodes now. When 4 sends to 6, the 6 finds it is a new one, and so it just adds 146 and forwards it. Alright. Now, so we finished all 2 hops. There is nothing left after 2 hops. So we go to the next set of rows. And those are 5, 6. And if you go back to the figure here, you can notice that there are only 3 nodes at 1 hop, which were in the first set of rows. Now there are 3 nodes at 2 hops, 7, 5, and 6. So let's see. We finished. Okay. 7, 5, and 6. So I think I may have to put 7 here. I probably missed 7 in this whole set of rows. But we have 5 and 6 here. Okay. You can see that we have 5 and 6. So let's finish 5 and 6 and see why 7 is missing. Maybe 7 should send out something. But anyway, so 5 and 6. 5 will now, 5, it got 1 message from 2 and got 1 message from 3. So the message that came from 2 will go to 9 and 8. The message that came from 3 will go to 9 and 8. And, sorry, message that came from 3 will go to 2, 9, and 8. Message that came from 3 will go to 2, 9, and 8. Message that came from 2 will go to 3, 9, and 8. Right? So that's what is going to happen. So I think there are few missing here. Few lines missing here. 5 to 8, 5 to 9, 5 to 2. 5 to 2 will be discarded. Right? Where? 5 to 2 will be discarded where? If I had a 5 to 2 line here, it will go to 2, and what will 2 do there? Anyone? Well, 5 to 2 will have 4 hops, and 2 already has 1 hop record, I mean 2 already has 1 hop record. So when it receives from 5, is it all making sense? You see, 5, the record that it received from 135, it doesn't know that it went to 2. I mean, it doesn't know that 2 already knows about this thing. So it will send to everybody which is not in the route. So it will send, so this message which came from 135 will go to 2, 9, and 8. Right? At 2, that message will be discarded because 2 has a better route. At 9 it will be kept, and at 8 will be kept. Similarly, the message that came from 2 will be sent to where? Will be sent to 3, 9, and 8. Right? 3 will discard it because it already has a better route. But 9 and 8 will do something with that message. Now, let's look at 7 and 6, same thing. So 6 will send it to where now? 6 will send to, because the message is coming from 1, 4, 6. 6 will not send to 4, it will just send to 8. Right? And let's see, 7. 7 was totally missing in the table, but 7 will send to 9. Right? So those are the rows. So I will have to, what I have to do here is I have to add 2 or 3 more rows in this set here. One will go from 5 to 2. One will go from 5 to 3. And then one will go from 5 to 7. Sorry, that was 5 to 7? No, sorry, 2 to 7. 2 to 7, sorry, 7 to 9. Sorry, 7 to 9. So basically, at this, yeah? Yeah, right. But here, I think the reason I'll tell you why I was saying you have to go. The message that came via 2 has a number 2 in the record. It will not go back to 2. The message that came via 3 does not have 2 in the record, in the route record. In the packet, there is no 2. The message says 135. Right? That message will go to 2. And that will be longer path. And that will be discarded at 2. You agree? Okay. Similarly, the message that came from 125 will go to 3. And discarded. Now, optimizations are possible. By the way, people are optimizing, and one optimization is that 5 could figure it out that really 3 is towards 1 somehow, and I shouldn't be sending anything back to 3, and blah, 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 this message is coming from 1. So those optimizations are possible, but if we just follow the simplest rule, then you send to everybody who is not in the record. Okay? And you could make one more rule that, okay, if it is not in the record, is this node already, shorter, longer, whatever it is, right? So you could optimize it. And there are many papers which are on optimization of AODV and DSR. Okay? So we will just keep it simple right now, consistent. And the simple thing is that you don't keep any other thing other than the route, what is in the packet. Okay? Everybody agrees with that? Make sense? So the whole state is in the packet, and so you look in the packet. If the node is already there, you don't send it to them. Otherwise, you send to all your neighbors. And in fact, one could even violate that rule and say, okay, I won't look up anywhere. I will just send it to all my neighbors anyway. So 135 could go back to 3, and 3 will throw it. That's also possible, right? But I'm just putting that right now that okay, because it is already there, it will be dumb to not look at that record. When you are modifying it and doing everything with that field, you might as well look at that field. Alright, so what is missing from this table here is, let's see, 5, 6 and 7. So packets starting from 7 going to 9 is not there. And packet starting from 5 going to 2 and 3 are not there. I think 6 is all set. Everything else is all set. Now, yeah. And you notice one more thing here, that there are 2 packets going from 5 to 8 and 5 to 9. Why there are 2 packets going? Because the 2 packets were received and they were equally good. One was 125 and one was 135. You see? So this is another difference from what you had in the previous one, AODV. So now parallel paths are being built by this method. You see now, if you go back to the previous slide, 8 has 2 parallel paths to 1. 8, 5, 3, 1, 8, 6, 4, 1. Alright, so 8 knows both the paths and it can use either one of the 2 paths. Whereas in AODV, it will know only one of the 2 paths and will just use that one path. You see, and that is the reason for sending these duplicate 5, 8, 5, 9s, so that all parallel paths get built. As long as they're equally good, we forward them. Alright, now let's look at 8. Now, so 8 received 2 packets. Remember, 8 received 2 packets which are good. So it is going to send 2 packets. So 8 sends to 6, 9, 5. 6, 9, then 5, 9. Why 6, 9? So 8 received a packet from this here. So it will send that packet which came from 6. It will send to 5 and 9. Another packet it received from 5. It will send that to 6 and 9. Okay. So those are the packets. 8 to 6, 8 to 9. This is the packet that came from 5. 8 to 5, 8 to 9. These are the packets that came from 6. Actually, one could draw a line from here and say, well, these 2 packets belong to these and this belongs to that. So you just have to make sure that all the packets that were forwarded somehow are forwarded correctly later on. Okay. So 3 packets were sent to 8. 1, 2, and 3 here. And if you see in the second set of rows. However, 1 was discarded. Let's see. Record forwarded. 5 to 8 was forwarded. And 5 to 8 was forwarded. 1, 2, 5, 8, 1, 3, 5, 8. And the third one is 1, 4, 6, 8. 3 were forwarded. 3 were forwarded. And 1, 2, 6, 8. 1, 2, 5, 8. And 1, 3, 5, 8. Okay. I think I should see here a few more in the third row. You know why? Because for every packet that was forwarded from here, we have to process it in this section. And we sent 3, 1, 2, and 3. So there should be 3 here. And what I'm missing here is, I think, one of these 2. So 1, 2, 5, 8, 1, 4, 6, 8, and 1, 3, 5, 8. So, one of those is missing. So anyway, so we put those rows and keep building like this. Anyway, so what will happen at the end is 10 will receive many packets. Here I'm showing 10 receiving 2 packets, 9, 10, and that path is 1, 2, 5, 9, 10, and it receives second packet, which is 1, 2, 7, 9, 10. 1, 2, 5, 9, 10, 1, 2, 7, 9, 10. I think one which is missing is 1, 3, 5, 9, 10. 1, 3, 5, 9, 10. This path is missing. So you will have 3 packets here at 10. Right? At 10, you will receive 1, 3, 5, 9, 10, 1, 4, 6, 1, 2, 5, 9, 4 hops. See, this is 4 hops. This is 4 hops. And this is 4 hops. Right? There are 3 4-hop paths, 3 equally good paths. So it will receive those 3 packets. Right? It will respond to all those 3 packets. So this is the response part. This is the route reply. All those route reply will go back along the path that they came from, and they will all end up at 1. Right? So now one knows there are 3 ways to get there. 1, 2, 7, 9, 10. 1, 2, 5, 9, 10. 1, 3, 5, 9, 10. And all other paths are longer. So these are the 3 paths. And it can choose any one of those 3 paths. Alright, sorry about this. Basically, this has been done so many times, but this is kind of, you sometimes miss some of these rows and columns. But the idea is just to count 2, 3, and 4. So we have to have 2, 3, and 4 here. At least once, all of them. Then we have 5, 7, 5, 6. We have to have 5, 7, 5, 6. Twice we have to have 5. We have to have 7 once and 6 once. So we missed the 7 in this set. Then we start with 3 8s, and I have only 2 8s, because the right way to do this would be I will just make an arrow from this 8. This will result in these 2 messages. This 8 will result in these 2 messages. This 8 will result in these 2 messages. So if you have those arrows, then you know that you missed 1 8, and you can go on like that. Okay, and obviously because this is visual, at least for the homework, although you cannot do it in a computer if it was to be implemented, but in a homework you can see whether you're getting all the paths or not. And if you're missing a path, you know that you're missing something somewhere. Yeah, question.
We have from the reply we have from 9 to 7.
9 to 7.
9 to 5.
Yeah.
We don't have from 9 to 8 because it has.
Okay. So the Dali here, and he's asking a question that where is the response from 9 to 8? 9 to 8. The reason there's no 9 to 8 because that path was not short and was discarded. You see, 9 to 8. It says, if you go to this row, it says 9 to 8 R rec, length 4, duplicate ID, longer path, discard. So it never reached basically, it was discarded at 8. Now, your question was, when this question related to which row now?
Not there, because
right now in this picture, we have shown only 2 replies going back.
Yeah.
And the replies have the path in them. Original path. And those paths were, let's see, the paths were 1, 2, 5, 9, 10 and 1, 2, 7, 9, 10.
Yeah.
So the replies go back along that path. Right? There should be one more which would have been 1, 3, 5, 9, 10. That will go back along this path. That will still not make 8.
Yeah.
So this is another thing, is these last things which are R reps, they just go back along the path that they came on. They are not broadcast. See, this says forward.
Yeah.
Right? Actually, maybe I should differentiate between forward and broadcast. So these are just going to one place. Well, actually, these are all going to one place anyway. So, alright. So basically, so the idea is that once we know the path, when you reply goes back along the path. Okay? All right, go ahead, Mark. One. Okay, that's a mistake. Good. That's the wrong one. Okay, let's see. That's another bug. That should be, it is going from 8 to 9, and it came to 8 from, let's see, this 8 is the very first one, which is 1, 2, 5, 8. Right? As the one, right? 1, 2, 5, 8, it is going to 6, and then it is going to 9. So 1, 2, 5, 8, it should be 1, 2, 5, 8, 9. Am I correct so far? And similarly, the row below that is also wrong, which is 1, 1, 3, 5. It should be, let's see. So now this is 9 to 7, and this came from, this 9 to 7 came from this 9, 5, 9. So it will be 1, 2, 5, 9, 7. Okay. Okay, so what is due now is that I have to re-prepare this table and email it to you guys again. But this is the 4th revision of it so far. And some bugs are still there. Anyway, I mean, now it's good that you can figure it out and you can fix it to yourself, which is good. So if there is any other bugs you see, please let me know. We have plenty of time. It's not a problem. And I want to make sure that you understand the differences here. The main difference is that you get multi-paths. Every packet that is equally good is forwarded, right? In fact, there is a slide coming up in a minute. And then you have to really account for basically all the packets, and the route is in the packets. So, good. Any other question about this? Yeah, go ahead. When do not forward? 5 to 3. Why did I not forward to node 3 from 5? From 5, I will forward the message 1 to 5 to 3, I will, right? The message that came, so here's the message. This message came 1 to 5. This should go to 3. No, so you're right. I already told you this is a bug. I have to add that row. Yes, I have to add a row here, which is 5 to 3. Huh? Over here in the right in the bottom. Here. Yeah. Okay, good. All right, because that one never made it. See, the thing is, I'm just following this path. 1, 2, 5, 9, 10, 1, 2, 7, 9, 10. The message which is 1, 3, 5, 9, 10 did not make it in this table. Yeah. So, okay, hold on. Okay. Let me just say, there are 2 rows here, 9 to 10, right? There should be 3 rows. One row which is missing would say 1, 3, 5, 9, 10. That packet, if it was there, it will result in a whole set of rows here, and that will follow 9, 10, 5, 3, 1. Okay? Answers your question? So if I put one more row here, then I will have few more rows here. Okay? So here is what I think basically, you found a bug which is good, and what I have to do is I have to redo this table, send it to you guys again before your homework is due, because this is part of the homework. And so I will send it out today. And basically, if there is still a bug, let me know, but hopefully that will be bug free. This table is fresh. I mean, I just made it myself. Okay? And that's why we are, running into these issues. Does that answer your question at least for now? Do you understand? Okay, good. Any other people see any other thing here? Basically, at the end of the day, what will happen is that 10 will know that there are 3 ways to go to 1, and 1 will know there are 3 ways to go to 10. And everybody on the way will know all the alternatives. For example, 2 will know that there are 2 ways to go to, 2 ways to go to 10. And 5 will know that there is only 1 way to go to 10. Things like that. Everybody will know how many parallel paths are there. Whoever is in the path, not everybody. Whoever happens to be in the return path. Okay? Good. Yeah, go ahead. Yeah.
Question. Is the communication from 3 to 9?
Yeah.
Let us say. So is there a sense of forward and reverse in the sense that whether 3 will send to 1 also?
Okay. So the question here from Love is that if 3 wants to send to 9, Now 3 already got this path to 10 and 9 and everything else in the table someplace. Would it send it to 1? Well, the thing is, if the path is valid, it's just going to use the entry as it is, and the entry will say that the 9 is 2 hop away and 359 is the path, right? But if path times out, then it will have to start from fresh, and in that case it will send to 1 and 5. A request.
Yeah, request.
Right? Yeah. So the paths can time out. If the paths time out, then they will send a request to all the neighbors. But if the path is not timed out, then they will use what is in information in the table, and that will save them time as well as, messages. Because otherwise the messages are delayed if you have to find the route. Okay. Any other question? All right. So what happens if the transmission fails? Route maintenance. If a transmission fails, a route error is sent to the source. It contains the host of both ends of the link. And this is important to know. If suppose 5 to 9 fails, then that message saying that 5 to 9 has failed will be sent to 1. Now, 3 will know that every path that goes 5 to 9 is gone. Now, in this case, there are not that many paths, but if there was another path, then those will all become invalid. Anything that uses 5 to 9 will become invalid. So it's not just this path. There are many other paths in the table. They will become invalid. And that's the point of this message, this line here. That the error message contains both ends of the link. Intermediate nodes remove or truncate all routes with that link. Okay. Source may reinitiate the route discovery. So if it loses all the paths, it will have to redo it. If it has some path, it will use that one. Now, caching is good and caching is bad. Normally we feel, oh, you have multiple paths, but caching multiple routes results in a faster recovery because you don't have to send another request, but the route may be stale. Okay, it may be old route and so, you don't know. And not only that, because you tell other people that I have this route, their information becomes bad. If you have bad information and you give it to other people believing it is good, so that is called cache poisoning. Now, unintentional cache poisoning, because this guy had an old route and he sent it to other people. Now, other people believe in the same bad information. So this is cache poisoning. So not suitable for high mobility environments. So the places where the routes change very fast, where people are always moving, you don't want to use DSR. Okay. Caching helps if the information is stable. If the information is not stable, caching hurts. That's the point. Okay. And then there is a source route overhead in each packet. Each packet has a source route overhead. And so basically every packet is longer. And on the wireless and on the low speed links. So now you can see why DSR was, AODV was added to ZigBee. DSR is the older one because you don't cache anything, and then you just have shorter tables and shorter things and packets. Okay. So any question on this slide? All right. So this slide summarizes the difference between the two, DSR and AODV. Yeah. Question. Is it a question? No. Okay. AODV versus DSR. In DSR, a single RREC can result in routes to several destinations. So that's good. Not only several destinations, you can get several routes to the same destination as well. In DSR, all error messages are sent to the source, not broadcast. So many nodes are unaware of the failure. So that's another thing, is that you see, if 5 to 9 breaks, only 3 will know, nobody else will know. All right. Route discovery is delayed until all cached entries have been tried. So if you have cache, that actually delays the bad news because you think that you have the information. Right. So not good for high mobility environment. So this is a table which does the same thing all over again. Routing table, you keep the route, you keep the next hop in AODV. Packets, you keep the route. In the packets, there is no route, just the destination. Replies, you get multiple replies. In AODV, you only get first reply, right? So you don't have multiple replies coming back to you. Route deletion in DSR is local, where in AODV it is global, and therefore it is slow because it is broadcast to everybody that okay, this this link is bad. I mean my route to so that was always the disadvantage of distance vector. If you remember the comparison between distance vector and link state, the problem is that the distance vector has this count to infinity problems. So basically it is slow. By the time everybody knows that the route is bad, it takes time. So the bad news travels slower. Here it is faster, but it is local only. Not everybody knows it. So the question is whether you really want global. If you want global, that will be quite some time before people will know it. And in these environments where people really don't need to know everything, and they just need to know when they need to know, and things changing so fast, it's your pick as to which one you like. But right now, basically, as I said, the AODV is slightly preferable. Any question between the two? If not, then we go to two more routing tables which can be used in two more routing entries that can be used in routing methods that can be used in ZigBee. And one is tree hierarchical routing. So if you remember the tables we have, remember the formulas we had, and we had given the sub range, etc., etc. If you have that sub range thing assigned, then you know exactly where in the tree who is where. So if you want to go, let's say from 12 to 30, you can calculate that. First of all, you send it to your parent if it is, you always send it to your parent. So parent 12 sends to 11, and the 11 says, okay, this is not my child, 30 is not my child, so it sends it to its parent. So it sends to C. C says, yeah, 30 is my child, or whatever, grandchild. So it sends to R4 because it knows exactly who will have that range, right? And R4 says, yeah, this is my child, and it sends it to 30. So because the addresses are very coordinated, you know exactly which child will have that number. Right? Is that clear? So this is very simple hierarchical table, hierarchical routing. If 30 is not there, too bad. If R4 is not there, too bad. You don't have to worry about anything. You just send it there, and if they makes it. If it's not there, there is no other path. There is only single path to everyone. Really, so there is no mesh as such. Not at least mesh topology. This is a tree topology. Okay, so this is allowed. And then one more routing which has been added in the last version, Pro version, and that is many-to-one routing. And that is what they need most often in the concentrators. In the concentrators, they need to have the data sent to just one place from everywhere in the world. So that is the sensor data collection. You have all these routers and sensors, and everything has to go to D. And from D, it will go to a gateway to the wherever internet it is going to. And so the gateway has large memory, can hold all the routes, all the nodes, but each node only remembers the next hop towards the gateway. So everybody just knows their parent, if you want to call them that. So A will send to B, and B will send to C, C will send to D, and it will reach D. And similarly, everybody is actually basically a child of D. And so this is another special case of if you want to call this previous one tree hierarchical routing, where the destination is always the root. Okay. So then there is one more recent version of ZigBee, and there is right now kind of competition between various sensor networking protocols to grab the spaces, as much space they can get. One very competitive space is super grid, or smart grid, smart grid. And we saw Bluetooth has a Bluetooth smart for smart grid. ZigBee has ZigBee smart for smart grid. Now the second space where ZigBee has competition is for the remote control, and this was basically the area where ZigBee started. So now they have this new version called ZigBee RF4CE. RF is radio frequency for consumer electronics, RF for CE. Right? And so the two organizations merged and they made a standard which is different. That's the main thing, is that which is different than the regular ZigBee. So the name is same. It's just like Bluetooth Smart is different from Bluetooth, but the name is same, and so they're just trying to capitalize on the name here. And so they operate on 3 channels, only 15, 20, and 25. Now I don't know how the 25 came in, because I thought there were 20 channels. But anyway, so 15, 20, and 25, I will have to double check those numbers, in 2.4 gigahertz. And so it doesn't run in at those other frequencies that Smart Grid wanted. Smart Grid wanted 900 megahertz because they want long distance. The remote control people who are remote controlling really the television in your home, they don't want to go very long distance. So 2.4 is good enough. So this is 2.4 gigahertz. Maximum file load is 127 bytes, which is good enough for them. So they don't need any fragmentation, reassembly, etc., etc. And then they only have 2 devices, remotes and targets, right? And the thing is that then there is a reverse feedback, though. I mean, right now you don't get any feedback on your remote, but with this ZigBee remote, you can see what is the status of the television. So the feedback, because it is a digital communication, you can get all the information, all the status, etc., on the remote. You can page the remote from the TV, so you can find out where the remote is missing and where the remote is under the bed, or under the pillow, or wherever. And pairing, a remote control works only with certain devices, so you make sure that you can your one TV doesn't start when you try to start the other TV. So all that can be fixed in the remote with this one. So this is a ZigBee RF4CE. Taking some key features of regular ZigBee and special cases for this. Okay. All right. And then there is a special case of the same thing, continuing actually along the same line. You could have a multi-TV remote. So you could have one remote that operates 3 TVs. And so for that, this is a topology which is allowed. And there will be 3 pans in that case. One pan, the TV is the coordinator, and then the remote is a leaf or whatever. Another pan, the TV is the coordinator. The other TV is the CD player, let's say, in this case, example here. And the third one is the DVD player. And so these are different pans. But this remote is a member of all the 3 pans. Okay. So this is how basically this will become a multi-device remote. The pairing basically is important part. So the pairing can be done by several different methods. One is that it could be built into the factory. If Sony sends you the remote with a TV, they will put that TV number in the remote, and you will be able to control that TV with that remote, or that model with that remote, something like that. And if you buy a remote separately from some other place, then you will be allowed to put that, and then there will be some kind of negotiation. So there are many different ways of pairing. One method is that you push buttons on both the devices at the same time. If you push the button on both devices at the same time, then they will pair each other, they will look for each other, and they will find each other. There are methods where you put some number on one, and just like you do on the Bluetooth, and put that number on the other one. So each remote has a ID, etc., etc., and then when you receive the command, it checks if it is allowed. If it is allowed, then it accepts it, otherwise it rejects it. Then there is ZigBee, sorry, and before I go to ZigBee Smart, any question about RF4CE? None. So we move on to ZigBee Smart. And ZigBee Smart is actually, as I said, is for the smart grid. And smart grid includes power supply, as we know, electric supply, but also includes energy supplies, gas, water. And these meters have to be read. Their problem is they want to read the meter while driving on the road. They don't want to come into your house to read the meters. So they need at least, few hundred yards or a few hundred meters distance wireless. And so ZigBee needs, ZigBee uses that. ZigBee can be used for that. and ZigBee actually is designed especially at 900 megahertz for that reason, right? So that you can go longer distance than 2.4 gigahertz. So it is developed in collaboration with Smart Grid Communication. Now the problem is Smart Grid is a big community and everybody wants to be in that. So actually it is not just for ZigBee alone. There is a home plug people, Wi-Fi people, Bluetooth people. So basically with everybody else. And because everybody else is there, they all decided to use IP. And that's the major thing. Now IP, if you use IP, now let's go back to original ZigBee stack. You notice that the ZigBee main contribution is the network layer. So you're not going to use the ZigBee network layer, you're going to use IP. That makes a major change to ZigBee. Now then ZigBee is stuck to the top part only, mostly application framework. So the ZigBee Smart is obviously not compatible with regular ZigBee. If you had a regular ZigBee device, it will not understand IP. And if you have a ZigBee Smart device, it will not understand regular ZigBee because it will not understand ZigBee routing. And but like everything else I told you, the name ZigBee is there, and they are happy, and that ZigBee can be used for smart grid. It's just a different ZigBee. Okay, so everyone understand the difference between ZigBee Smart and ZigBee? ZigBee Smart is IP based. So the routing layer is gone. Alright, that brings us to the end of this series of ZigBee lectures. And the 6 key points. ZigBee is for Internet of Things. An Internet of Things is what we call sensors, industrial automation, remote controls, etc., etc. So it uses 15.4 for Phi and Mac, but it provides its own routing, its own transport, and its own application. So these are the top 3 layers, right? And since it does routing, etc., it has an addressing. There are 2 ways of addressing. One is stochastic, and one was that distributed. Stochastic addressing is just random one. Now ZigBee Pro is the latest one, so therefore it supports the stochastic routing, many-to-one routing, which was that concentrator thing. It supports fragmentation, and it supports mesh topologies. So that is really mesh where you can go find your path, whereas the previous ones were more tree-based. A number of application profiles have been developed, and they are called end points. So there are end devices and end points. End points are the applications, and the endpoint application 0 is GDO. GDO is that domain objects, ZigBee domain objects. Those are the management points. Application support layer provides data and command communication between the applications. So basically, applications profiles have been defined. The data types have been defined. Groups of data types, clusters have been defined. And so all those things are all standard, and you can quickly put together an application using those profiles. The network layer provides addressing and routing. The addressing can be assigned using distributed or stochastic schemes. Routing is by AODV or DSR, T-hierarchical, or many-to-one. So there are 4 ways of routing. AODV, DSR, T-hierarchical. AODV is for mesh, T-hierarchical is for trees, and many-to-one is for concentrators, right? And then ZigBee has RF4CE and ZigBee SEP2. So that was the name of ZigBee Smart. ZigBee Smart, I didn't use the word SEP2, but SEP2 is Smart Energy Protocol version 2. So ZigBee Smart is ZigBee SEP2. So there is ZigBee R4CE, ZigBee SEP2, and ZigBee. ZigBee is the original ZigBee. So these are designed specifically for, whatever they are said. So actually I should add one more. It's designed for remote control, smart grid, and IoT respectively. Third one. There are three things here. And so we say remote control, smart grid, and IoT. Homework 13A is the distribution assignment. And while you are on the distribution assignment, I did change this slide as I proposed before on numbering, because there are too many subscripts here and the subscripts were really not meaningful. So I removed all the subscripts. There is no change as such in anything except that the symbols now look cleaner a little bit. The numbers are all same. So if you download the new PDF, you will get this slide rather than the everything with the subscript. So the answers will remain the same though. So there is a homework number 1. Homework number 2 is the AODV, and you have the latest one which is correct. And 3 is DSR, and for DSR I will have to send you one more corrected one, but you know where the mistakes are. So those are the 3 homeworks. The reading list here is twofold. This book is very good. Actually, I should put threefold. I'm sorry. There are 3 things to read. I forgot to add one more. So this book, and then there's a book by my friend Garg. Okay. So the second book, which was I had pointed out earlier, Garg book, that I would add to the reading list. So that you have to read. Actually, that is where the best description of DSR and and the AODV is. And the third thing is this lecture, my lecture on 6LoWPAN and RPL. Now 6LoWPAN and RPL are IoT protocols. We would have discussed them here in this class. However, we are really running out of time and I have really more important things to teach you. So what I'm doing is taking the liberty for you to read this, which I just taught last semester. So this is very fresh. I could just repeat it here. So you see, there is this lecture which I just prepared last semester, and it is all recorded and everything else. So rather than using the time here in the class, I could play back that lecture right here in the class even today, but I decided that it's just better that you can read it at home. You can listen to it at home. And the next Monday when we meet, if you have any questions, please ask that question, and I will maybe allow up to Wednesday also. You can tell me whatever. And then with that lecture will be part of the exam.